A parallel plate capacitor has a capacitance of 451. That's interesting, like 451 Fahrenheit. Never mind, not important. 451 times 10 to the negative 9th farads, so like 451 nanofarads, I think nano. The separation between the plates of the capacitor is D, 0.550 millimeters. Okay, that seems reasonable. What is the voltage difference between the two plates of the capacitor when the charge on the plates is a magnitude of 9.06 times 10 to the negative 9th coulombs? What is the magnitude of the electric field between the plates and the capacitor? Okay, so some things to think of here is there's a few formulas you should know. The one we're going to start with is for capacitance. So the way I write this is Q equals CV. The mnemonic I use for it is actually QVC. It was a home shopping network. Watch it on TV, make the phone call, buy things. So if you can remember QVC, and then you put the equal sign between the Q and the VC. The Q, that's the charge. Some people write it as a little teeny q. V, voltage, and C is capacitance. So capacitance is based on the geometry of what you're looking at. Parallel plate, spherical, cylindrical, whatnot. And then the dielectric. We're going to assume that the dielectric here, we don't need to know dielectric because we're just given the capacitance straight off. So we don't have to find the capacitance from the geometry and dielectric. So we're just given that for this parallel plate capacitor. One thing to note is that charge Q is measured in coulombs, which have the unit C, while capacitance is measured in farads. It'd be kind of natural to think that, oh, C, coulombs, that must be capacitance. No, gross conceptual error, human performance trap. Try to avoid that error. Okay, so now that we have this, we're trying to find for, what is the voltage difference? So all voltage is a difference. And writing the difference there, even though I like it when people say voltage difference, it's kind of redundant. So voltage. So V equals, so don't let it throw you off that the word difference is there. It's good that it's there, but all voltage is a difference. Okay, so we have rearranging, we have voltage equals Q over C, which is, let's see here. We don't know the capacitance, do we? Separation between the plates and the capacitor is 0.55. Parallel plate has a capacitor. Okay, here we go. There we go. So we have, and then we have a charge. Sorry, I should clean this up a little bit. There we go. So we have, the charge is this, and the capacitance is that. So we take the charge, 9.06, times 10 to the negative 9th. That's coulombs, so I'm going to leave off the units for now. And then we have 451 times 10 to the negative 9th farads. And you could try and rearrange that and make that like, I don't know, 4.51 times 10 to the negative 7th. But I want to leave it as 10 to the negative 9th because I think that something's going to cancel. And so we cancel that, and we are left with, let's get our calculator. Calculator, clear. 9.06 divided by 451, and we get 0.02. That's going to leave it 0.02 volts. Okay. Which equals 2 times 10 to the negative second volts, which is 20 millivolts maybe? Okay. So now we got that part. So that's the first part of the question. What is the voltage difference between the two plates? Okay, so now we want to find what the magnitude of the electric field between the two plates are on the capacitor. So the formula we're going to use for this is voltage equals negative integral E dot dl along some sort of curve. Now, if you're taking calculus-based physics, electromagnetic physics, then you should absolutely memorize this. Pal, write it out 50 times, 100 times on pieces of printer paper, whatever you need to kind of sear this into your brain, into your soul, so to speak. But with that said, if you're not taking calculus-based physics, then kind of zone out for a couple seconds till I get to the kicker, the result. So one thing to notice here, this is a vector, and that's a dot product, is an electric field in a parallel plate capacitor is constant. No matter where you are within the electric field or between the two plates, it's going to be constant. So we're assuming that between these two plates, we have a constant electric field. And so what that means is we can pull it out, the electric field here outside the integral, and I'm going to assume that the path we're going to take is straight across. And no, that's not straight. Pretend it is. And therefore the dot product will be 1. And so we're left with negative E integral dl, which is just going to be the length of the curve, which will be negative E times distance. So for a parallel plate capacitor, let's see, we're trying to find the electric field. What is the magnitude of the electric field? We look at this part, we look at that part. So if you're not in calculus-based physics, you can say that electric field equals negative V over D, where V is in voltage. It's convenient that voltage has a V for a symbol and the units are V. Very convenient. If I could redo all physics, I would make things like that more common. Okay, so we know what our voltage is. It's 2 times 10 to the negative second volts. Now I'll leave off the V. We know it's volts. We need the negative there, and then our distance, we're given something in millimeters. So I'm going to say 0.55 times 10 to the negative third. I'm going to change this to 20 times 10 to the negative third. And so we have, 0.55. Rewrite this one more time for clarity. So 20 times 10 to the negative third. That's same up here, 20 millivolts. 0.55 times 10 to the negative third. Cancel, cancel. And we have, calculator, 20. Wait a sec, I'll just do second answer. Second answer times 1,000. You get 20 divided by 0.55. We have 36.52. 36. There we go. 36.52. And this will be 36.52. And this will be volts per meter, which is convenient because we know the formula over here is volts per distance. So this will be volts per meter, where in this case the V is the unit and not the, voltage. So the V represents voltage, units for voltage. And then M is meters, which is a unit for distance. So it makes sense that that'd be the units, and this will be the answer to the first part. Okay? Excellent. I know it's a little bit challenging. Second semester physics, electromagnetism always seems to be. Okay. Second part, charge Q1 of negative 5.4 times 10 to the negative 6 coulombs is at the origin, and a charge Q2, negative 2.2 times 10 to the negative 6, so micro, is on the x-axis 1 meter to the left of Q1. So I'm going to assume that this is 1 meter. And I'm going to assume that when they say left, they really just mean right. If Q3, which is that positive charge, and is located on the axis at 0.75, so we'll call this 0.75 to the left, I'm going to say right, of Q1, what is the total force acting on it? And here I'm going to assume that it is Q1. If Q3 and is located on the x-axis to the left of Q1. No, I'm going to assume that's Q3? Yep, I'm going to assume they're trying to they're trying to get us to find the forces acting on Q3. Especially because the hint, find the force acting on Q3, find the force acting on Q3 again, keep track of all directions. Well, yes. Yes, we will keep track of our directions. Okay, so I'm going to clean up the board real quick. And so what we're going to do then is I'm going to look at Q3. Oh, they already drew other pictures for us. Very convenient. So if we look at Q3 right here, Q3 is going to be attracted to Q2. So we're going to have force electric 3, 2. And then we're going to have force electric 3, 1. And since they're opposite charges, Q3 and Q1, Q3 and Q2, they are going to be attractive. And so from there, we're going to then find the forces in each direction. And since they'll oppose each other, we'll make sure that we subtract the two. Okay, so to find force electric equals K Q1 Q2. Even though I write Q1 Q2 here, I really don't mean Q1 Q2. I mean one Q and then another Q. So what I'm going to say here is this would be force electric 3, 1. And so this will be Q3, Q1, and then this will be the distance R 3, 1. Okay, and then I'm going to do the same thing. Can I copy paste that? I could, I'm not going to though. Force electric 3, 2 equals K, which is Coulomb's constant, Q3, Q2 all over R 3, 2. So let's see here. I'm going to start solving this one real quick. So this will be K, which I'll leave as K right now. Coulomb's constant is like 8.99 times 10 to the 9th. Don't know what the units are, but they're standard SI. And we want Q3 and Q1. So Q1 is 5.4 times 10 to the negative 6th. So 5.4 times 10 to the negative 6. These are supposed to be squared. I forgot that. And then Q3 is 1.6 times 10 to the negative 6. 1.6 times 10 to the negative 6. And then we're going to have R, and the distance between 1 and 3 is 0.75. So I'm going to do 0.75. I'm going to make sure it's in meters real quick. In the axis, meters. Yep, 0.75 meters, which is useful to know. So that'll be squared. Yep, I'm going to leave it like that. Yes, I'm going to leave it like that. Okay. And then we're going to subtract off from that over here, which will be K Q3, 1.6 times 10 to the negative 6. I remember that. And then Q2, which we were given up here, 2.2 times 10 to the negative 6. 2.2 times 10 to the negative 6. And you notice here that I'm neglecting the negative signs. It's because I don't care. 1.25. I just use the positive and negative signs, the charges basically, to determine which direction the force is. So what I do is I solve it for the magnitude, ignoring the negative signs, and then I put them together in a logical manner. You'll see in a sec. So solving this out, we're going to have K times 5.4 times 1.6 all over 0.75 squared minus, and that minus has to do with the signs because I know that these two forces are opposing each other. And I'm going to assume that this one's positive. This is the one going to the left direction. So if I get a negative number, the actual total force is actually going to be to the right. 1.6 times, go like this, 2.2 all over 0.25 squared. I'm going to do this real quick. Move that to the outside. Let's factor it out so my math is simpler. And we have 1.6K times, calculator. Go to calculator, on, clear. So 5.4 divided by 0.75 squared minus 2.2 divided by 0.25 squared. And that gives us negative 25.6. Negative 25.6. We'll multiply by 1.6. 1.6. We get negative 40.96. Negative 40.96. Now, K is the Coulomb's constant. You can look it up. I like to use Wikipedia for that sort of thing. So K is 8.9, I just know this off the top of my head, times 10 to the 9th. And then there's some units involved. I should know those, but I don't. You get away with not knowing them. at least not having them memorized. So we'll take this answer times 8.99 times 10 to the 9th. And we get, divided by 10 to the 12th. And our final answer is going to be negative 0.368. Make sure real quick. Yep, negative 0.368. So what I forgot there was, when I factored things out, what I forgot to carry, or keep with me, were these guys right here. 10 to the negative 6 times 10 to the negative 6. And so this should actually be times 10 to the negative 12th as well. So when I divided by 10 to the negative 12th, that's the same as multiplying by 10 to the negative 12th. So 10 to the negative 12th, that is the same as 1 over 10 to the 12th, like that. So that's what I did with my calculator. Find out what we found real quick. We're finding force, and so this will be newtons. And so, force net. So since I had the force 3-1, which is this portion right here, I had that as the positive, and I got a negative answer, which means that the negative for this would actually be this direction. So it's the opposite of what I had as the positive force. You can choose either one, as long as you kind of understand what you're doing. Keep it consistent. So the net force will be to the right of 0.368, which you could call the same as the force is in this direction, but it's negative 0.368. Same concept, same idea. Because a negative vector is just flipped 180 degrees. And this is actually a vector. Find the force acting on it. Okay, so to recap this one real quick, what we did was we used the equation force equals K Q1 Q2 over R squared, where the one Q is from one charge, the other Q is from the other charge. K, right there, is Coulomb's constant. You can just look it up, it's just a constant. 8.99 times 10 to the 9th is the SI units. And then R is the distance between the two. And then you square that. This bears a striking resemblance to the equation you have for force of gravity, which is gravitational constant, mass 1, mass 2, over R squared. So if you can remember one, you can usually kind of use a mnemonic to find the other one. So that's how I would approach this problem, and hope that helped. I will see you next time.